Okay, today's lesson is on the atmospheric heat budget. So we're going to start by doing what we already know. What do we know already? Well, we know that the atmospheric layers are the thermosphere, the mesosphere, the stratosphere, and the troposphere. In between each sphere is a pause, called the tropopause, stratopause, the mesopause. At the very top, there's another layer called the ionosphere. We don't need to know that. But one thing we do need to know is that as you move upwards in terms of layers, the temperature gets colder, temperature decreases, then the temperature gets hotter, colder, and warmer again. So temperature is variable among the whole atmosphere. All right, the other thing we need to know is composition, or we should know. What do we mean by composition? Well, we mean by what gases it's made of. So we know that nitrogen make up 78% of all gases. Oxygen makes up 21%. And then we've got our trace gases, mostly argon, which is 0.9%. And then it's all of our other little bits and pieces. Carbon dioxide, 0.04%, and then we've got our other trace gases. I'm just going to write trace, 0.06%. Okay, so when we think about our heat budget, we've got to think a bit about it in terms of inputs and outputs. Inputs. So inputs is where our heat comes from. All right, so where does our heat come from? Well, of course, the only place it can come from is the sun. The atmosphere gets 100% of its energy from the sun. And this comes in the form of solar radiation. Solar radiation, which we use a term called insolation, and that's incoming solar radiation is where those words come from. Generally, the form of radiation that we get from the sun is in what we call shortwave energy. Comes in the form of shortwave. All right, now when we think of shortwave energy, that normally comes in the form of ultraviolet and visible light. So that's our shortwave energy. Let's draw a little diagram of that. Here's the surface of the Earth right here. And let's draw that incoming solar radiation. All right, excellent. So this shortwave radiation, we need to label it as shortwave. I'll label it here. Incoming shortwave. Excellent. Now, if we think about shortwave, why do we say shortwave? It's because it's on the, if we think about the electromagnetic spectrum and electromagnetic waves, essentially we're looking at different types of light, and we're looking at the very shortwave side of that spectrum. All right, excellent. That's the first bit. Now, when shortwave radiation arrives to the Earth, it hits a surface. Now, it could hit a couple of different surfaces, but when it hits a surface, it is transformed into a different type of radiation. It's actually transformed into long wave radiation, or sometimes called infrared radiation. That will come across to us as heat. So let's draw this in now. So I'll write this down first. When shortwave radiation hits a solid object, it is transformed. This is infrared. Or thermal heat. And that's important, that last bit, that thermal heat. So solid objects transform shortwave radiation into long-wave radiation. So when these waves hit something solid, transforms into heat energy, which is then radiated back from the surface. That's our long wave. So if we think about this incoming solar radiation, it doesn't just hit the surface, it actually hits some other objects as well, like little particles of atmospheric dust, or it might hit droplets of water. And when it does, those shortwave radiation actually releases heat into the surrounding part of the atmosphere. So incoming solar radiation not only warms the surface of the Earth, but it also warms the atmosphere itself because it's hitting solid objects there. Okay, great. That's the first little part. Let's get on to where this energy goes. All right, so here's my diagram, and what I've done is I've drawn in 100% of heat energy arriving from the sun. Here it all comes on its way into the Earth. It comes in the form of shortwave radiation. So where does that energy go? Well, let's look at this in terms of percentages. It can be very confusing because if we look at it in terms of amounts, the amount of heat energy that's distributed around the globe is different in every different place that you go. So that's obviously depending on latitude, and I'll talk about that in just a second. But let's look at this. So we will start by talking about the heat radiation, well, that's absorbed by the atmosphere. Remember the small particles down here? They absorb some of the energy, and they absorb 23% absorbed by atmosphere. So we know that the atmosphere is made of particles. There are lots of different things in this, in the atmosphere. There's atmospheric dust, there's salt, there's clay particles, there's water droplets. They can all absorb water. So there's 23%. Another part of this is, I'm going to draw a little cloud here, because this cloud's going to represent what's happening right here. And 22% is actually reflected by clouds. So actually some of the heat is reflected back into space before it even arrives on the surface. 7% of all insolation is reflected by the surface. we're going to talk about that in a moment because that's very important. So if we add these all up here, well, we've got 52%. That leaves 48% of the initial energy that rises from the sun hits the actual surface of the Earth. Now, this can vary. This is a generalized, this is a very generalized heat budget. It depends on where you are. For example, if you live in the United Kingdom, somewhere where it's overcast all the time, well, then a lot more of that insolation is going to be reflected by a cloud cover. If you lived somewhere like the Antarctic or in the Arctic, where it's very lots of ice, then a great deal more is going to be reflected by the surface. Conversely, if you lived somewhere where there was a great deal of volcanic activity, quite a lot of it is going to be absorbed by atmospheric particles. So this is a generalized heat budget. It is, I guess you could say, an average for the globe. Now, what happens to this heat? Well, actually, a lot of this heat makes its way back and forward and bounces around the atmosphere. And that's why we're going to talk about the greenhouse effect a little bit later. But I wanted to talk first about this little part here, reflected by the surface. So some of this reflection depends on something called albedo. Albedo is the ability of a surface to reflect heat or insolation. The ability of a surface to reflect insolation. So if we think about objects that are darker in color and objects that are lighter in color, well, we automatically know the situation. I guess you go in summer, you put your hand on a white car, it's not going to be as hot as if you put your hand on a black car. So we'll write that down. Different surfaces will absorb different amounts of heat for example, ice sheets or snow have a greater reflection. Areas like forests, they absorb. So I guess you might be wondering, why do dark objects absorb more heat? Well, let's ask that question. Why do darker objects absorb more heat? Well, the answer is because they reflect less. Those darker objects absorb more of the wavelengths. They absorb a greater scan of wavelengths than those objects that are lighter. Because they don't reflect as much energy. They absorb that energy. They absorb more energy and release as heat. Now this becomes a bit of a problem, and it becomes part of what we would call a feedback loop. A feedback loop is when once something might start and then its operation starts encouraging more of that operation. And I'll give you an example. if we think about the world that is covered in ice, the world that is covered in ice will obviously reflect a lot more insulation and therefore will be colder. So it will remain colder. It's a lot difficult. It's very difficult for it to warm up if it is constantly removing all of the insulation that it's receiving. Okay, so that's the atmospheric heat budget. What I suggest you also do is, and I'll draw it in this corner here, and that's to talk about angle of incidence. Just understand that different surfaces of the Earth receive different amounts of incoming solar radiation. So at polar regions, that same amount of energy that the equator receives has to cover a much wider area, so therefore it receives a lot less energy. So that's the heat budget for today. What I'd like you to do also is, if you want to have a look at your textbook, page 140 to 143, have a little read, and that will do us for today.